Awesome. Welcome everyone to the RSK Community Call for October. I'm joined here today by Diego Massini, Adrian Heidelman, and Sergio Lerner.
Hi.
Hi everyone, and I'm Brendan. Okay, so the primary topic for the community call is going to be RSK Improvement Proposals. There is an entire collection of them, and we only will be talking about a few of them in this call. Some of them are in a completion state, some of them in a discussion state. And today's session will also feature an announcement about RSKJ, the RSK node. You can scan the QR code that you see on the slide to jump to the links that you see on the slide in case you're using a mobile phone. Okay, so let's begin today's agenda. So we'll start off with an introduction to the RSKJ v3.1 release by Adrian, and then we'll talk about aggregation and parallel transaction processing. That'll be done by Diego. And finally, we will do a RSKIP about roll-up optimized ephemeral call data by Sergio, and then we'll wrap up with some Q&A. The link for this particular community call is the one that you see on the screen and the QR code, so check that out, and let's begin. So there are other places that you can reach out to us as well. So you can check out the RSK Community Slack, which looks like this. It's a chat group, and if you're a developer or you're interested in ecosystem or events, etc., you can just check out this thing. But for those who are attending this call, we recommend the Research and Innovation channel, which is specific to RSKIPs and other things that the Research and Innovation team does. The other thing that I encourage all of you to check out is a more extended long-form communication in the format of a forum. If you've used Discourse before, you might be familiar. So RSK Research, which is on research.rsk.dev. To get to that one, click on or scan this QR code. All right, and I'll just do a very quick recap of some of the announcements from the July community calls, about 2 community calls ago, when we released or were about to release the RSKJ 3.0.0, which was significant because it was a hard fork. I bring this up again because the RSKIPs that were part of that release have all been finalized just recently, and so they've all been merged into the main repo. So if you'd like to see that announcement again, check out the YouTube link. Also, the Iris adoption has gone smoothly, and virtually everyone has adopted Iris now. So again, I'd like to, maybe Adrian, you want to talk about the difference between a hard fork and a non-hard fork here?
Yeah, absolutely. Basically, very briefly, a hard fork introduces new consensus changes, so that those kind of releases are mandatory releases for all who adhere to these consensus changes. So everyone needs to update their nodes and download in the latest RSKJ client, which in this case of Iris was 3.0.0. In the case of other releases that are not network upgrades, they are not mandatory. So each node operator or developer running its own node can decide if they want to update or not. We usually encourage users to do so, but it's not mandatory.
Yeah, excellent. So if you primarily are after performance upgrades, you'll get them, but it's not compulsory. So we recommend it, but your old previous nodes will still continue to work. And yeah, this is just more information on that. So today we'll be talking about the 3.1.0 release, but before that, I just wanted to sort of highlight that these community calls are an effort to get more of the community involved in order to get more feedback, to discuss any consensus changes in particular, and also talk about the formal process for proposing improvements. In this community call, we will not be discussing RSKIP 0, which is the actual process. But in our previous calls, we have discussed it. So watch the replay. These will happen periodically. We aim for about once every 1 month or 2 months, thereabouts at the moment. And yeah, that's the focus of these calls. So, Adrian.
Right. Thanks, Brendan. And yeah, so following up with what Brendan was saying, so we thought it would be valuable for the RSK community that we'd spend some time during these community calls to update on the progress and the news related to the development of the RSK client. Brendan just briefly mentioned that there are usually or there periodically releases of the RSKJ client, and the releases that get most of the attention are the ones related to network upgrades, of course. But there is a lot of work done and features added more often to the RSK node that are not consensus changes, but relevant anyway. So we believe it's worth mentioning at least very briefly in this space, so developers and node operators are aware of this and can decide if they want to update their nodes or not. And also looking to get more feedback and more involvement from developers in the maintenance and the evolution of the RSK client, which is something that we can probably promote by talking a bit more about it, especially in these open spaces. So as we have just mentioned, or Brendan has just mentioned there, we have recently released only a few days ago, actually, a new version of RSKJ, which is 3.1.0, which is a non-mandatory upgrade, but brings several improvements, especially in performance and in enhancements in the JSON RPC interface, which is the interface by which users and apps can interact with an RSK node, as you probably know. For example, to query information from it, to send transactions and things like that. So quite a sensitive and important component of the technology. And just a very quick comment on the versioning numbers we use, because we've been asked a couple of times about this lately, about the numbers, 3.1, what do they mean actually? And yeah, just wanted to mention it very briefly about that. We use a typical versioning scheme to assign unique versions numbers to releases, using these 3 numbers that is usually called major, minor, and patch. And the first number is the major number, and network upgrade releases are indicated by increasing the major number, which is currently 3. So when a new hard fork client is released, this number will be increased to 4. So next network upgrade version will be 4.0.0. The number in the middle is the minor number, and new non-breaking features increment the minor number, such as in the case of this latest release. And the last one is the patch number. We increase it when the release only contains fixes to bugs or security patches, but no new features or consensus changes are introduced. So that's not that frequent, but it has happened anyway. So just wanted to mention that to clarify a bit about these numbers. So what's new in 3.1.0? As I said before, on one hand, there are several improvements to the JSON RPC in order to improve the compatibility with Ethereum client nodes. We have added support for the new pending transaction subscription. So you can now subscribe to notifications that are triggered whenever a transaction is added to the pending transaction pool of the node. We have added support for the EIP 1898, which basically adds the possibility of querying some methods like get balance, get code, get storage, add, and a few more, using a block hash as a parameter, which is something that was not possible before this. There is also a new method called Debug Trace block by hash, which returns the stack trace of all the invoked opcodes of all transactions in a block, which is quite useful for debugging tasks. And there are several small fixes about compatibility that are usually related to having return values comply with the JSON RPC specifications. If you have been developing with RSK, you may have find some obstacles there, or things that do not match with how information is retrieved when using, for example, an Ethereum client node. Right? So we've been fixing all that stuff, and hopefully there are no remaining ones like that. And on the other hand, there are several performance improvements, as I said, mostly related to how the node stores and retrieves certain data structures. There are some improved caches, and basically we are constantly trying to fine-tune these kind of things so the node can reduce block execution times, and that we are able to execute more transactions in the same amount of time. There are several things we are analyzing related to performance and scalability. The research team in IOB Labs is working very hard on this, and I believe Diego will present some ideas we have for the near future about how to scale the RSK network and as I said before, be able to process more transactions per block or per second. It's important to mention that some of the improvements in 3.1 came from Gitcoin contributions. We ran an RSK hackathon not that long ago. Probably Brendan can tell a bit more about this, but there have been some contributions coming from that hackathon that are now introduced into 3.1. And there were some contributions from the QB3 team also working on the chain integration. So thank you very much to the developers that worked on this and also that reported issues that let us improve the quality of the RSK node. And that's very briefly what 3.1 is about. You can always get a detailed list of the changes introduced in each release by accessing the milestone page on the GitHub repo for RSKJ. So there's the link on screen. What you will find there is basically each one of the pull requests that have been merged and included into this release and every RSKJ release actually. And again, this is not a mandatory release. It's not mandatory to upgrade to this version. But as we said before, we always encourage users to do their or to update to their nodes to the latest version. Finally, we are currently within IOB Labs working on version 3.2.0, which we expect to release most probably in around 1 month. That would be end of November or probably early December, and with several new improvements in hopefully in performance and stability and gas estimations enhancements, which is something that has brought some obstacles for DApp developers, and a few more things that hopefully we will be commenting about in the next call. So that's basically it. Thank you.
Awesome. Thanks, Adrian. I just wanted to sort of chip in a little bit there about the community contributions. So it's great that we've got a lot of contributions this time around. I know, the Gitcoin hackathon participants who contributed, I think it was mainly the RPC related improvements. So they after the hackathon, like about a month later, they were like, oh, so when is my pull request going to be merged and released? I was like, unfortunately, there is a Iris release coming up, so there's an embargo on performance improvements and interface improvements, and so you'll have to wait until the next release. And so I was like, hold on, okay, and now it's finally happened. So pretty happy that we're able to announce that.
All those contributions, we need to review them. Then we need to rebase everything and have them merge into the changes that we are doing. So it's it's a bit of work, but it's amazing that we're having developers from outside IOB Labs bringing new changes to the code.
And if I'm not wrong, Adrian, every single commit gets a security review, right? Apart from the normal review, it gets a special security review, right?
Yeah, absolutely. So that makes the development life cycle a bit slow, let's put it that way. But we believe it's what we need to do. So every single pull request is reviewed by our security engineers, and yeah, we want to be sure that we're not introducing any vulnerability.
Okay, great. So, and I just wanted to highlight this. Then the sheer number of pull requests in this release is 43. So that's a big a big release. Yeah, awesome. Okay, let's go on to Diego.
Yes, thank you, Brendan. Hello all. Well, I want to share with you the two projects we are working on at the research and innovation team in IAB Labs. One is aggregation, which essentially is a fast and cost-effective peer-to-peer payments. The idea is that the aggregation is a layer 2 scalability solution for Rsca. And the main idea is to execute transactions off-chain and periodically post those, not the transaction itself, but some transaction data and validity proof to the blockchain. This way, we can say that the layer 2 is secure by the blockchain. And we can transact much faster than if we do directly on the layer 1, which is the blockchain. We investigated here two potential approaches. One is optimistic rollups. The other one is zero-knowledge rollups. The method of verification is the key distinction between these two approaches. For zero-knowledge rollups, the idea is to generate cryptographic proof that can be used to prove the validity of the transaction or the transaction data sent to the layer 1 using smart contracts. And on the other hand, for optimistic rollups, the idea is to introduce a challenge period where any participant in the network can provide fraud proof. If no fraud proof is presented during this challenge period, then the transaction data sent to the layer 1 will be considered valid. So these two approaches, the two of them have some drawbacks. For zero-knowledge rollups, the drawback is the generation of the validity proof because it's a complex and time-consuming process. The verification is fast and efficient, but the generation is complex and requires some computing power. And the drawback for optimistic rollups is the duration of the challenge period. That means that we cannot consider a layer 2 transaction final until the challenge period is complete without any fraud proof being sent to the layer 1. For this project, we analyzed different implementations of these technologies, such as ZK Sync, Starknet, and Arbitrum. We finally decided to go with the zero-knowledge approach because we think that finality is an important feature to have. And in this, for our first milestone, which happened last quarter, we were able to port ZK Sync version 1 to Rsca. It is not public yet, but it's working. And this version of ZK Sync allows users to mint, transfer, swap RBTC, ERC tokens, and NFTs. In future versions, the ZK Sync team is working on enabling arbitrary smart contract execution. We will continue working on the analysis of the next version and also exploring other solutions and looking forward to collaborate with the other teams working on this space. Yeah, that's it for aggregation. Brendan, if you can. Yeah, thank you. Parallel transaction processing is the other big project we are working on at the moment. It has to do with what Adrian mentioned, also with scalability and being able to process a block as fast as possible. That doesn't mean that we are going to change the block generation rate. It just means that we will be able to process a block much faster, so we can include more transactions in the block per second. So the idea is that at the moment, Rsca processes transactions one by one from each block in a unspecified order. This is because two transactions that are applied in different order could produce a different final state. However, most transactions do not share state. There are some independence. And therefore, those transactions could be parallelized without any interference. Following up with this idea, we could split the transactions into partitions, which each partition could be executed in parallel. One possibility that we were analyzing, and there is an RSKIP for that, is that miners could process transactions in a serial order and at the same time analyze these dependencies to discover these partitions and create an execution index. Full nodes then can later use this index as a way to decide which, not to decide, but the decision is already made, but a way to execute these transactions in parallel because they can trust that there are no dependencies between these different partitions. And for this project, our main goal is to process as many transactions per block as possible, but also to reduce synchronization time. The most important challenge of this project, as I mentioned, is the minimization of the overhead introduced by this dependency analysis. And at the moment, we are evaluating different options. And the next step is to do some benchmarks to understand how this potential solution behave and if they actually improve the processing time of blocks in RSK. And that's it.
Awesome. So this is still very much in the research stage or research and innovation, and so this is a great time to put ask questions and add comments and suggestions. The best places to do that would be on the RSK community Slack, and of course on the forum as well, research.rsk.dev. So next up we have Sergio, who will talk to us about RSKIP 281, and I believe that you have your own slides.
Yeah.
Is that right? Okay.
Yes. Give me a minute. I will share my screen.
Yeah.
Chrome tab. Share. Okay. So I have to put in present mode, I suppose. Okay. Right. So do you see the full screen?
Yes.
Okay. So I'm going to present research that started in 2016, started a lot of years ago, about the optimization of the layer 1 to handle side chains, to handle essentially rollups. But back then, of course, there was no pressure. There was not many attempts to create rollups on top of blockchains. But at those times, for me, it was pretty clear that we needed a way to provide a data availability layer for rollups that was optimized. And what started in 2016 with several RSKIPs, it evolved with the evolution of rollups until we get to this new RSKIP, new proposal, which is very, very efficient, and I think it can provide a lot of gas savings for rollups. So this is RSKIP 285 of rollup optimized ephemeral call data. Okay, so what is this ephemeral call data? This is some data that you post in a transaction similar to the call data, and it gets a discount in gas cost to be only temporarily a variable for smart contracts to query this data. So essentially, you have two flavors of this ephemeral call data. You can remove by default the data after some time. So basically, initially, it's cheap. But if you want to preserve this data, for instance, you want to query this data later, then you pay an additional amount of gas to preserve the data. And then this is another flavor, which is called keep by default, where you initially pay a high amount of gas, or the standard amount of gas to keep the data, but then you can decide, you have a period to decide to remove this data from the blockchain, and then you get reimbursed for this data that you have removed. And what are the use cases? Well, the best use case for this technology, this improvement, is rollups, because rollups needs two things. First, needed data. In case of optimistic rollups, you need data to be available in the blockchain for a certain period, which is called the challenge period, right? But after the challenge period has elapsed, most of this data, you don't need it anymore. There are many multi-party protocols where you need to post data to the blockchain and during the challenge period, but then after the time, then the information is either not relevant or it can be compressed. And that's what I will show you that happens with rollups. Okay, so you have some data that you want to put immediately available in the blockchain so that all the clients can reconstruct the state, but at the same time, in a later state, you want to compress. You have a function that can compress this data, and then you would prefer to throw away all the previous data. Okay. So at this point, Diego has talked about rollups. I'm pretty sure I don't have to argue in favor of rollups to the ecosystem, but there are many advantages of using rollups and growing the stack using rollups. So I think that the most important is that you are free to experiment. So every layer one, as time passes, it gets more conservative. Changes are harder. The community does not want to risk more. So rollups have always been the way to experiment. Maybe it was the same notion of sidechain in the beginning. Now it has moved into the rollup space. So you had the freedom to experiment. You can inherit layer one security. You may create your own governance tokens to create a smoother path for the improvement of the rollup, where most layer one, most blockchains do not have any kind of governance tokens. Then this kind of having separate rollups allows more easily collaboration or more easy integration of different solutions, because each team is focused on their own code. So it gets, kind of very good for decentralized improvement of a stack. And then you get every rollup can be optimized for a different need. Okay, you have a rollup that is optimized for payment. You have another rollup that may be optimized for smart contracts execution, and then you have these possibilities. So I think that at this point, without going into the details of the pros and cons of rollups against scaling the layer one, I think that rollups are inevitable, right? So it is something that we are going to see growth, and we have to make our blockchain the best layer one, the best data availability layer to allow these rollups to flourish. So what is this L2 cold data cost? What rollups spend the gas into? So basically two things. There is a constant cost about committing some block, some layer 2 block into the layer 1, which is split between a fixed cost, as I said, which is in case of zero knowledge rollups, is the verification of the validity proof of this data, and the other cost, which is variable and depends on the number of transactions, is the cost of transaction data on the layer 1 for having this data availability property, so that every user can reach the same state and make sure that the transaction has been correctly considered. Okay, so what does this transaction data contains? It contains basically the standard values, the from, the to, sometimes the fee, either if it's contract call, it contains additional call data, but it contains signatures, right? And signatures takes a lot of space. But you know that once these committed transactions have been accepted, then you don't need the signatures anymore. If there is no challenge to this state, then why are you still storing those signatures? So many layers 2 use some kind of signature aggregation mechanism like BLS or START, SNARKs to aggregate all these signatures and do not post it on the first place, on the first place, right? Just post some proof that the signatures exist, but do not send the signatures to the blockchain. But optimistic rollups, they have to send the signatures to the blockchain. There is no way out. So if you take a look at the Arbitrum code, you will see that there is a compressed ACDSA transaction type, which is the most common, I think, that posts the full 65-byte signature on chain. And if you take about the equivalent in ZK Sync, then there is an object called transfer op, which does not send the signature, which is much better. And all the different values that are posted on chain are compressed as much as possible. For instance, addresses generally are not posted in full, but they represent an index in an address table. And amounts are compressed using standard scientific notation like a Mantisan and exponent, okay? But each L2 is slightly different. So I'm going to show you what information does L2 post. For instance, this is the information posted by Arbitrum, and it's pretty large. So you have the sequence, which is kind of unknowns, the gas price, the gas limit, destination, call value, call data, the full signature. And it takes about a little bit more about more of 81 bytes, okay? And if you think about a token transaction, which I think will be the best use case, the killing application of layer 2 will be token transaction like stable coins and Bitcoin transactions. And if you take a look at those transactions, then the call data also needs the function selector of the ERC20 token, the destination, which is not compressed, and the amount, which is also not compressed. So now a token transaction posted on chain, it takes 137 bytes, okay? And let's take a look of a ZK Sync transaction, token transaction, and this is much more compressed. So you need still an opcode which sets which kind of transaction this is, the from, the to, the token. These are all indexes in tables. The amount, which is packed in only 40 bits, and the fee, which is also packed in 16 bits. So that's only 20 bytes. Okay, so it seems that ZK rollups are much more optimized and will on the larger scale it will cost a lot less. Okay, so I think that this is why Diego talks about the preference for ZK for zero knowledge rollups over optimistic rollups. And if we take another L2 transaction that is posted on chain, for instance, Fuel, which uses a completely different model, which is UTXO. And if we assume a standard, let's say 1.5 inputs and 2 outputs, because the number of inputs on average is between 1 and 2. So let's say 1.5 inputs and 2 outputs for the transaction, then it consumes 121 bytes. Then it's a lot. So what if we just we just could post the state changes? Okay, the difference in the change in state after we have processed hundreds of thousands or tens of thousands of transactions. Okay, so a state change is just an account ID, the token ID, and either the balance or the compressed balance, like the delta, the change in balance. And so that's only 16 bytes. Okay, so you get the idea that posting state changes instead of transactions, you get highly compressed information. And if we think about Arbitrum and make this generic, like to be able to post any contract storage cell change, then you can still put all the change information. For instance, in the case of an ERC20 token transfer, you can still store all the state information in about 17 bytes. Okay, so clearly that's a lot less than the 137 bytes that originally you require for the transaction data. So here we have to take some, to see how this information can be compressed, we have to create some model of how payments will work on the real world, right? I've analyzed several models, but I've put here just the simplest possible model, which is not so far away from reality, but just to show you that, let's say there are n accounts, and this is a payment rollup. Each account performs 30 payments per month, like one payment per day, to some other account at random from the account set. There are no specific accounts that get a lot of payments like merchants. No, this is plain simple. Any account just pays for a random number of 30 payments made to a random other accounts. And at the end, if you had to post at the end of the month state difference between the previous state and the new state, then you would consume 5.5% of the information that it took to post every single transaction on chain. And if you think about it, this is kind of realistic. But if you think about the space consumed by, let's say, the Ethereum blockchain, which is a terabyte, right? I think, yeah, and the state of the Ethereum blockchain, which is about 40 gigabytes or maybe more, or 60 gigabytes, then you get the same ratio. So this is kind of very realistic. So yeah, you see here that this translates to a payment cost, which is asymptotically, like without taking into account the fixed cost, this would be 20 times or a little bit less than 20 times lower. That's a lot. If we think about Arbitrum token transfers, ERC20 token transfers, then the gain, the reduction in cost is much higher with the same model. Like you get a cost that is less than 1% of the original cost if you could just throw away all the transaction data and post only the state changes. In the case of token transfers, is not the same because the UTX model in itself, it produces a lot of state. It removes state and creates state all the time. So here the gain is not so good, but yet you get a transaction cost that is 4 times less. Okay, so it pays. So now that I have explained the motivation, how this works, how you can actually add information to the blockchain and then remove it later. So first of all, a new field is added to a transaction. There are several transaction formats we can adopt to add a new field. Of course, the best would be to adopt the Ethereum, the transaction format that Ethereum has adopted in the last hard fork for extension of the transactions. But we have our own proposal for the same. And then this new field contains a lot of other fields. But basically, what you can see that the Ecd, which is the ephemeral call data, instead of being hashed into the transaction, is double hash, right? It's hashed first with Kejak, and then the Ecd standard hash is hashed again when you create the hash of the transaction that needs to be signed, right? This double hash gives the opportunity to remove the original data without changing the transaction ID, because this transaction data you can remove it, and of course doesn't change the transaction ID. While if you would like to remove the data of a transaction, then of course you would never be able to reconstruct the transactions and get the same transaction ID. Okay, so yeah, at this point, I will just focus on that. There are some other fields that I will explain are important, but the one of the important fields is the Ecd size. You have to specify the size of the information that you may later remove, because if it happens that you remove it, you still need to be able to compute the cost of this data, and the cost is related to its size. So you have to have a specification of the size. Also, you have to specify if you want to keep this information by default or remove it by default after some time. and some other fields, which are this hasher contract address, hasher call gas consume, and ACDC hash, which allows you to create a user specified hash function for this data. You have not only the standard Kajak hash function, but you can also use your own custom hash function. And this is very important for ZK rollups and also for optimistic rollups. So what are the current costs of a call data in Ethereum and in Rsk now? So pre-Istanbul hard fork, Ethereum, the cost of each byte was 68 gas per non-zero byte, and this was the same in Rsk. But in Istanbul, Ethereum reduced this cost to 16 gas per non-zero byte. And the thing, the curious thing about this is that there was no actual, resource change or optimization that was made possible to reduce that amount. They just thought that this was needed to reduce the cost of rollups, and they thought that the node was good enough to handle this, so they did it. But I think that's not a very scientific way of handling this. I think that you should only reduce the cost if you have a plan or a technical improvement that actually removes the actual storage or handling cost of that information. So the proposed cost for RSK with the new ephemeral call data is 8 gas per byte. Probably you cannot get lower than that for some other reasons, but you would get a 50% discount compared to Ethereum. But this doesn't mean that we are going to reduce the call data for all other transactions. This will be just the ephemeral call data that the gas cost will be reduced. So if we take the current gas costs in Ethereum and in Rsk and you compare it, then you will see that in Ethereum, the cost of a layer 2 transaction, the minimum cost would be 16 cents. Consider the data that needs to be paused. And in case of Rsk, using ephemeral data, it would cost 0.038 cents. Of course, this is because the transaction cost on Rsk it's lower now. Okay, so how does it work internally? Okay, internally there's a new precompiled contract. It's called the Ephemeral Data Manager that has a registry of all this data that has been posted. So the solution proposed by this RSKIP is a mixture between some part written in either a precompile or even Solidity. It could be written Solidity, and the other part is more entangled with the consensus, right? So if you want to register your call data, if you want to either persist or whatever you want to do with the ephemeral call data, you have to register first. So a contract must call this function from the ephemeral data manager, which is called the register ephemeral call data. And you give an ID. With this ID, you are able later to either remove it or query it, right? And this ID is formed by the concatenation of the sender, the contract that decides to register this data, and an ID that is chosen by this contract. Okay. So if you do not register the call data, then this ephemeral call data is removed instantaneously. So there is no, even it's not present in the blocks while they are propagated. Okay, so you can create that in your transaction, but you will just be paying for that data, and that data will be immediately removed. So you need to register it. So once you want to remove it, if it is not a remove by default data, then you have to request the removal of this data, and then you would have to call a method that is called request removal of ephemeral data, giving the same ID that you use to register the ephemeral data. And a third step is needed after a confirmation time has passed, where you actually remove the data. So this happens 30,000 blocks after the data has been posted originally, you are able to actually remove it. Okay, this is to avoid that blockchain reorganizations messed with this data. That some nodes that remove the data need the data again after a huge reorganization of the blockchain. So the third time you call this with the same ID, you actually remove the data. And in the case that this is a remove by default data, then you have to do the opposite. You have to call a method called request persistence of the ephemeral data. You give this ID, and you get your data persisted forever on the blockchain. And you have to pay a lot of bitcoins to persist your data, of course. In the case of the persistent request, it's just one method. You don't need to call twice. So what is the workflow of this transaction commit, state commit, so that you can save this amount of data? So you first do this. This is what happens in a optimistic rollup. You first commit your transactions, then you have this challenge period, and for that period you need your transaction data to be present in the blockchain. Then sometime later, let's say 1 month later, you will post a state diff, and then you still need a challenge period so that anyone can say, no, this state diff you've posted is invalid, the same as the commit transactions post. So once that challenge period is over, then there is another confirmation period to avoid, the reorganization of the blockchains to mess with the data that has been removed. And then you can actually remove all these original commit transaction data that you've posted, and you only leave this L2 state diff, right? So I think I have some minutes to continue explaining what is this user-defined hasher. So there are some fields that are only applied to this user function that can hash the ephemeral data in different ways. And this is implemented actually in a contract. So you have to deploy a contract with your own hasher, and then you will be able, when you broadcast a transaction, to use that contract to hash your ephemeral data. Of course, this contract must be immutable, and it must be present before you broadcast your transaction, okay? So in the case of a optimistic rollup, you probably would want to create a Merkle tree so that your user-defined hasher is actually using a standard hash function, but creating a Merkle tree of all these rollup data. Why? Because it's highly probable that later, when a challenge is sent, you would like to be able to send to the blockchain the minimum amount of information to prove that there is a wrong state transition in one of these transactions. Okay, so what would happen in the case of an optimistic rollup? This is the life cycle of a commit and a challenge. Is that first you register with this register ephemeral data. This is the step 1, and the step 2, you would get this Merkle root, right? We're calling this function in the ephemeral manager, which is get current Ecd hash, and then you will store it. Let's say that you index by the block number, and you store the ID and this Merkle root. And at a later time, when any user wants to challenge this information, what he does is he sends obviously the block number, the offset in this Merkle tree, the offset in the data, or the leaf of the Merkle tree that he wants to be verified. So the contract retrieves this Merkle root and the ID. It can get actually the data from the ephemeral data, basically preserving the data forever, which this method called get ephemeral data, using this offset that the user has provided, and then actually it validates the data. So the fraud proofs can be very, very short. You just have to point to the place in the commit data where the information the transition implied by that information is wrong. Of course, 1 month later, you can actually remove the commit transaction data. Oh, of course, this data that has been queried, you will not be able to remove it. Another potential life cycle is that you use the Merkle tree itself, but you use only the root, and the user provides the Merkle inclusion proof. Okay, so this is another potential way of doing the same. In the case of a ZK rollup, then it's much easier, right? You first, in the case of a challenge, you just commit transactions, and instantaneously you can verify in zero knowledge the data, and then you post the state difference, and you verify that the state is correct using a zero knowledge proof. So there's no need for challenge. Then there is a confirmation period, and then you remove the commit data. So it's much easier in case of course, in case of zero knowledge proof. And what is important here is that you would choose a user-defined hash that works very efficiently for your zero knowledge system. Like we have, for instance, the Poseidon hash function. So by doing so, you get very, very efficient verification on of your transaction data, and so yeah, you get lower cost on the fixed part on the prover. You get lower cost for the prover. So as I said, the life cycle of a challenge response is that you first register in step 1 the ephemeral data, then you will use the user provide zero knowledge friendly hash function, and then you will store that in a local storage of the contract, the ID and this friendly hash function hash. And once somebody, once you need to verify this commitment, this is not a challenge, sorry, this is the verification of the commitment, you can retrieve this this friendly hash and verify it with your zero knowledge proof. Okay. So this ephemeral call data manager has many methods to help you either query the information or remove the information later. So this first group of methods are all to query these new fields that appear in the transaction. So as you can query, you know, the gas costs or the of a transaction, then these methods allow you to query these new fields. And then you have this other group of methods that allows you to get information of past ephemeral data. Okay, so retrieve old ephemeral data, remove it, some other stuff. If you decide to query this ephemeral data, of course, this data will be permanent in the blockchain. So you better make sure that you only query this data when it's needed. So to summarize, and just in time, this ephemeral data reduces the cost of rollups realistically by reducing the resources required by a node to handle this, compared with Ethereum that has some unrealistic reduction of the call data cost. So you can either remove it by default or keep it by default. It's not an easy change, that it requires several changes in parts of the consensus protocol. So obviously the transaction format, then the blockchain synchronization protocol must be changed to accommodate the fact that some blocks will come without this ephemeral data, and you have to still be able to verify based on something that will happen in the future. Okay, then you have this new precompile, and of course you need rollups to support this. It's not enough to deploy this feature on the blockchain. You need to program your rollups to support to make use of this feature. Also, it's interesting that this RSKIP competes with some other. For instance, it competes with RSKIP 115, which is ephemeral blockchain. Basically, this proposes that the whole blockchain, the past blocks are removed from the blockchain once a state snapshot has been included. So I think that we have to, of course, the community has to evaluate this RSKIP, but we also have to compare it against some other competing solutions. Yeah, that's all for me for today. I don't know if you have any questions.
Yeah. That was very, very detailed. I'm gonna do a share screen. One sec. Let me just put it back onto the. Sorry. Okay, I think we're back. Awesome. So your slides were for 285, right? Not 281.
Maybe I mistyped the number. Yes.
Okay.
What I wrote. Let me check. The number is 281, and I think I put 285. I'm very sorry.
Just clarify, yeah, because I know sometimes there are different competing proposals that are very similar. So I thought maybe, I think that was extremely complicated. I tried to follow along. I was a bit lost, to be honest, at the part about the multiple, two different hashes, the custom one and the standard one. I'll look forward to reading the actual RSKIP, which I suggest that everyone also does as well. The link is on the screen, and I believe we've just posted the link to the RSK Research Forum, the discussion specific to that one in the group chat. All right, so that brings us almost to the end of this community call. We'll just wrap up with a few more things. So the RSKIP process is something that we'd like everyone in the community to take part in. Strongly encourage that. And that includes you, an RSK user, someone who's building on RSK, or someone's interested in working with RSK. There's lots of interesting stuff that's happening like on the bleeding edge of blockchain and decentralized technologies. So this is a good place to propose and discuss that content. I'll highlight that there is RSKIP 0, which is essentially how to participate in the process. But if you haven't done one before, we strongly encourage you to check out the Slack community or the discussion forum, and we'll be happy to help. It's quite an active community. So I think we're running a bit over time, so we will do Q&A asynchronously. So go to the Slack and find this channel, ask the questions there, and Sergio, Adrian, and Diego, and others will chime in for sure. Okay, and for those of you who are on your mobile phones, we'd like to hear what you want to see discussed in the next community call. So I strongly encourage you to check out the entire list of RSKIPs that we have on GitHub in various stages of completion. And if anything piques your interest, please request that we discuss it in the next one. So you don't have to say, hey, I want to propose my own thing. That's not the only thing. You can also say, hey, I want to learn more about this that's already there, and we'll be happy to talk about it. So make your request in this thread. This QR code here will bring you to that link. Awesome. Okay, thank you very much.
Thank you very much, Brendan, for hosting it.
No worries.
Thanks.
And then thank you all of you for your excellent presentations.
Thank you.
Okay.
Thank you, guys.
Bye-bye.
Bye-bye. Bye, everyone.
Bye.
Ciao.